Hello everybody, today we'll be doing binary tree paths. Given the roots of a binary tree, return all the roots to leaf paths in any order. A leaf is a node with no children. So here we obtain two leaves, and therefore we develop two paths to this particular node. Now, this is a binary tree, and so you won't have two nodes pointing to the same node. That would be fairly interesting. I'm not sure if that's possible. I don't think that's possible here. Let's see. So the number of nodes in the tree is between 1 and 100. So the minimum, this is an edge case, is 1. Not 0, but 1 item. So those are edge cases. So I'm expecting a time of O of n, time for each node to be visited. And also O of, let's say, n space for like returning the node path. Well, technically there will be fewer node paths than the number of nodes, but as you can see here in the edge case, we see the same number of nodes as paths. There can be the paths will be reduced each time by a half with each like visit layer. So here's what I mean. So let's see, 1, 2, 3. Let's do 4, 5, 6. 4, 5, 6, 7. All right. So we have some nodes here, and here's what I mean by reduced. So we have 1, 2, 3, 7. So basically, it's basically a, and let's see what happens next. We have 8 the next layer, right? 8, 9, 10, 11, 12, 13, 14, 15. 15 items, but we divide that by half, as you can see. So basically, every step that we have is 2, 4, 8, and next one is 16. Next layer, but that means that it is log of n, because it's not just that we only double each layer. It's that, suppose the next layer has, let's say, 2 times 8, which is 16, right? We have 16 items here. So how many total items are there? The 32. There are 32 items. So basically it's n divided by 2 paths. And so basically that's O of n. Well, that's cool. That's nice to know. So a little bit more specific there. So we got the understanding here, and let's do a match. Match is basically a recursion. Usually that's what we do for like binary trees. And how we're gonna do it? Let's do a plan. What we're gonna do, here's the plan. Our plan is to visit each node and like get the roots.val information and build our string. Then visit the next 2 nodes. Once we reach a leaf node, basically root.left and root.right is none, then we append to our output array. So basically we need, let's implement output array, and we need a separate DFS call where we take in the root value, and the base case is that like basically we return, and if it's a leaf node, we have been building up our string, right? So what happens is that our output, not append. What we're going to append is our string that we have been building. So S plus the string of root.val, essentially, and we return. So once we hit a leaf node, we append that particular path of nodes, and we return. So now, lastly, so let's build this string up. So currently, we have a string. It's going to be an empty string. So it's going to plus equals. Well, we're going to add to it. Well, we're going to add root.val plus the arrow. And the last one does not have an arrow. And that way we get this particular string. So how are we going to keep going? So we're going to run dfs root.left. And we're going to append the string. And dfs root.right. And the string. With that, we run dfs on the root node with an empty string. And we have basically built up our output. And we can return it. Basically, this follows our plan. And we are ready to run the code and see what sort of errors we might get or not get. It looks like we didn't get many errors, and we are okay with the base cases. We are not okay with the base cases because we did not test the base case here. So let's test that. I believe it's okay because, like, the first item we build, and we built it and we returned it immediately. So let's submit and see how it goes. Perfect. So that's our solution. And did we get the O of n time? So for our evaluation. So evaluates, we did visit every single node. And lastly, we did go to, we're going to build, well, n divided by 2 paths, which is O of n essentially. And yeah, that's it. That's the problem. That's how we print all the paths of the tree. So let's think about another way to do this. Can we return items back? So basically this is a top-down approach where we return the string back. And what's wrong with that is that we only get the information back when we return back to this case here. And how are we going to retain all that information? Now that light is killer. Okay, so I'm going to pause the video and get rid of it. So this is how we can get to a certain point, save up that information, and build our string, which is perfect here. And with that, I hope you enjoyed this video. Like and subscribe. And if you want more videos, check the link in the description below. And of course, if you find another way of doing this problem, which is much cleaner, please share and so we can all learn together. Thank you very much, and I'll see you in the next one.